So we're gonna do a by request homework problem. But the announcement is and was that the homework and quiz are extended for a week and a half now. Yeah, due to various factors. Read your announcement at blackboard.com. So it was literally blackboard.com. So I actually did it correctly that time. Sometimes I just put .com at the end just because I think it's funny. Like weirdanswers.com, sphericalcoordinates.com. You know what? I, I don't know if that made the joke worse or better. But thank you for that. Are you one of those particular people that has to add the HTTPS on the front? Some people are very fanatic about it. Good. Yeah, and if you ever see someone saying it must have HTTPS on the front, just chill out. They need to chill. Oh, you use www? Man, how 90s of you. Anyways, so ta-da! We're gonna do this problem, and I don't know what the answer is, so I'm gonna get it wrong 3 times. Is that so wrong? Is that bad of me? Come on, tell me. Oh, it's totally fine to do what I'm doing, and then I want to see what's your answer here. Of course, we can just go to Desmos at this point. Um, let's think about it for a second, okay? I want to look at the problem. I want to think about it for a bit, and then we can go and do it here in a minute. This is how I would approach any problem where I don't know what to do. I get it wrong. I look at it. I'm like, okay. Then we can go back and look. So I can see that rho is equal to 1 minus cosine phi, and this is my rho. So that looks pretty good. We've got calculate the volume, cardioid revolution. It doesn't say first octant or anything like that, but and it's not. If I look at my angles, it's not. Okay. Oh, so you're confused about that guy. It's bro. You're saying that this is spherical. They haven't really mentioned much. So you're saying to me that you're assuming that they're wanting the whole sphere. They didn't talk about theta, so we're doing theta is 0 to 2 pi. That makes sense. So, but they didn't talk about phi at all. And so then why are we only going to 0 to pi? Beautiful question. I love this.
I have no idea if Chad's being serious or sarcastic. And now I'm a little
It's
nervous.
it's actually a mix. So go ahead.
No, I was gonna say it's a solo cup coffee.
Yeah, from the solo cup coffee. Yeah, I know. It's just because I'm going insane right now. No. Let me show you about spherical coordinates. Hi, perfect timing. So, ew, can't do it there. So we got my x, my y, and my z. We have theta goes around in a circle on the xy axis. So that's theta. We're all happy with that. But the phi is what is in question. The phi is coming down from the z-axis coming down. And then it keeps going down. And so this would be pi if it went from the top down to the bottom. Okay, cool. You're saying that no, it needs to come all the way back up. But I'm saying that theta has already accomplished that move for you. What's going on is you have, let's just say we have this slice here. Yes, this is my xy plane, and this is my z, and I'm going from the top down to the bottom. There's my pi. This is phi. So far, so good?
Yes.
What if I take this and I rotate it around 360 degrees?
Get your shape back.
It's like you have a slice of the orange, and then you make for a full circle of it, you will have your full orange.
Okay. That makes sense. I just couldn't figure out how they got just pi.
Right. So the limits in spherical would be, of course, starting at 0 always, 2 pi for your theta, pi for your phi, and then whatever radius you have. I'm just going to use a 1 because it's, unit, let's just say. 1, and then it's rho squared sine phi. I'm writing a q. It's not quite right. Phi d rho d phi d theta. So these are the standard values for a sphere, for an entire full sphere. Cool?
Yes, sir. That answers my question.
Perfect. And then that was it. So once you have this, to me, I'm just looking at it. It doesn't look too bad. I think there's like a U sub in there,
Right.
and I
So
don't.
you have the square right there, so it would be cosine cube.
Mm-hmm. Yeah, I would do a U sub with the sign and blah blah blah, and then it's done. So I'm not worried about that.
Right.
But you're cool now?
Yeah, I'm cool. It was just the setting up part.
Of course.
Issues.
Of course. So did I make it dramatic enough?
Yes. I would say enough.
Solo cup coffee. Indeed. Is that cool? Good. Good. Okay. Excellent. So yeah, that was a very good question.
Okay.
I was wanting to play it up
Okay.
because it's like such a fundamental understanding thing that I wanted to like emphasize, bold, italics, underline. Good.
Yes, sir. I'm good.
Perfect. Any other questions? The last question of 15-4. Hi. Then let's go. I'm all about it. Is it a mean question? Hi. 15-4. Go ahead.
Oh, I was thinking. I think I also got stuck on that one as well.
The last one? This guy? You don't like him?
No, it's just like I didn't understand.
You can say that you don't like him.
Okay.
Oh, okay. He's okay.
I understood how
Uh-huh. Okay. Okay. So I'm going to go through my standard, I don't know what to do, but this is how I do it kind of thing. Is that cool? All right, awesome. So I got it wrong 3 times, and I don't know what to do. And so I'm going to start with Desmos, because my idea, my concept, my thoughts here is that if I can find how to set up the limits, right, and set it up, because that's the main part here in Cal 3, right? The setup is everything. Once you get that, it just integrates whatever. So if I can find out how to replicate what they have, then we should be good, and then I can like go back and do it again next time. Is that an okay method for you? I mean, you did like a small head nod. You're good? Okay, good. Okay. Because like I don't want to be like if you had already tried what I'm doing. Oh, okay. I don't either.
Yeah, I was thinking like you'd change it from X to like the R cosine. Yeah.
So yeah, I haven't even read it. So we got a cardioid, we got a circle, and so they're wanting the region inside the cardioid, but outside the circle would be like the two two little humps on the heart is what I'm thinking. But let's check, or maybe it's going to be the little tip. You're right to graph it. You're right to graph it. That's a good thing. Oh. Okay, well, it's like a crescent moon. Is that what it would be? So it's inside the red, but outside of the blue. So it's this crescent moon shape. Am I right? No. Right. So that will go all the way up. So we got crescent moon going all the way up and down, right? And then it's cut off by this z equals x plane thing, which I don't know what that looks like yet, but that's the cylinder. So it's like a crescent moon cylinder thingy. Not cylinder, but half a cylinder. And then z equals x is a line. I mean, it is a plane probably, but I mean, who says that's a plane? It's a line. So, no, come back. And so whoop, and so whoop. Clear this whole thing out. Okay. So what we're faced with right now is this crescent moon shape like that. And in 3D, it looks kind of like this, but then it also does that up here. So it looks kind of like a crescent moon little right? 3D printed. It's not just 2D printed, it's 3D printed now. So what would it look like to have z equals x? Well, let me just draw that. So I got x and I got z, and if z equals x, it's like a line doing this. Yet, what's my y equal to? What is y for this? Anything. There it is. So going back to 2D again, I'm sorry, 3D. Going back to 3D again, x, y, and z. I'm saying that this line right here is kind of like coming up like this. And again, that that's that plane that we're talking about right here. I'm just replicating this guy right here. But y could be anything. So it could be right here as well, and it's down here as well. So it's just a plane, right? That plane is going to cut through this. Again, this was x, y, and z also. So I'm just going to replicate that now. It looks kind of like this, and cutting it off. So it's like a piece of paper that's cutting that thing off. So far, okay? The side of my crescent moon then would basically just be cut off. This is what it would look like on the side, and this is what it looks like from the top down. It would still have that shape, that crescent moon shape, but it's like I'm cutting it like that. So what we're starting to find is we have a top and a bottom for all these different things. Of course, how do I put that into cylindrical mode or whatever, right? Because we got r equals, so they're wanting to do polar, obviously. You know what? Timeout. What section is this? Did we have cylindrical? Not at the time. Good thing we do now. Good thing I talk about it again and again and again and again. But how would we accomplish this here? Not cylindrical, but polar, right? The problem is that when in polar mode, this is like we're stuck in a way. I'm saying, well, my area is the double integral d r dr d theta, basically, right? That's polar now. They didn't teach me triple integrals yet, Chad. Although I did. I'm just going to say I did, of course. So how would I accomplish this? Well, what you're not seeing, and this is from Calculus 1, is that all we need is a top minus bottom. R dr d theta. And so now what we had was a 1. And technically, if you want to be really specific, it was 1 minus 0, top and bottom. Now I have another top and a bottom that I'm going to do. My top, in this case, is going to be this z equals x thing, and then the bottom's, of course, 0. So I'm going to put that in. I want to say x or z. Up to you, whatever you want to use there, right? R dr d theta, because they're the same thing. But you had said it, right? In polar mode, we can change that. Just make it a r cosine theta. I am not 100% sure if that is a good move or not, because technically it could be z also, right? But then at the same time, z is that. Yeah, so let's see it before we actually go and try to solve this thing, which is not hard. Instead of trying to sit here for 5 more minutes, let's just go do the Desmos thing, right? Good talk so far? Okay, cool. So yeah, let's do that. Do the Desmos thing. Actually, I want this guy over here, so I'm going to do that. Integral from 0. No, we're doing polar mode, right? So 0 to wouldn't it be negative pi over 2 to pi over 2? Looking at my limits there, and then my r would be 0 to. Actually, it's not 0. It's from one to the other. 9 to the 9 plus cosine theta. And then I got r cosine theta times times r dr d theta, and let's compare that with what they have. Yeah, it matches. Okay then, so that's what we would do. We would now integrate it, be done, and we're good. Like for the other problem, we just start over. Is that cool? Do you like it? So blah 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 for 10 minutes, James solved it for you. Is that right?
My first thing is YCC. I'm like, let's just ignore double integrals. Let's look at triple integrals. If we only have one there for the other ones, we'll probably get d0 to x, and then switch it with the polar, and then work it from there.
All right, so you're saying this is the Wild West, and you're shooting from the hip.
Exactly.
You don't need to aim. Gosh, you're gonna hit something. Something will work. That's kind of funny. That's what it felt like to me. But now I told you this is the proper way to handle a firearm. Okay, you hold it up, you look down the barrel, and aim at what your target will be. Make sure there's no other targets in the way.
Are you sure? I kind of like to cover the eyes so you can hit the target like that.
Hold it sideways, and pow pow pow. But you know me. I am not a proper person, regardless. So, yeah. Any other questions? Do you like that it was extended? Oh, you didn't hear? Oh, you did. Okay, we're good then. So that was a good thing for y'all? Oh, okay. Not a good thing for you. I don't know. Because you procrastinate. That's funny. Good. Yeah.
Hey, Chad, do you know his dominant arm is kind of in a sling, right? So he has to write with his non-dominant arm.
Oh.
So I'm trying to give you an excuse, man. Take it.
That's funny. Okay. Then we're going to move on. So the idea is that we have to keep moving on because we got a lot left to do. But I do want to review for the exam when y'all want to review for the exam. Okay, so I'm not thinking that will be next week. I'm guessing the week after. Depends on when you want to take it. Okay, so we'll figure that out. Cool? I'm in the process of making the exam. It's just from practice quizzes, so you already know what to study for. Well, yeah, of course. So what I did so far is I took the practice quizzes and I just dumped all the questions in. And what I'm going to do is start categorizing it and pooling them. So, or removing ones that are not good test questions. So, this one here is not the one we're going to do. It's actually this one, but I already did it. So yeah. Sorry. Yeah, I normally do this on the instructor side, but I forgot today, and so I already did it. So I don't want to explain what I did here. I want to do it, but I'm going to do it with the answer here. Is that okay? Okay. So flash the answer. There's your answer. They're wanting to do the line integral. So anytime you got integral with a ds, it's line integral stuff for this function. And they're wanting to follow, what is this shape right here, this curve? That's a circle. So they want a circle of radius. Very good. First quadrant from here to here. Now, hold on for a second. This is x and y. If I'm looking first quadrant, that's this dude up here. And then where would this guy be? At what angle? What's my theta? Of course it is. Yeah. 45. They're wanting to go from here to there. From here to there. It's important to go from this point to that point. Otherwise, you'll get a negative, and then everyone's sad because blah, 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 and then I give you points back. As you know, you just flip your limits integration, you'll just change it to a negative positive, right? I'm not worried about that. But I want to make sure you see it now so we're picky today, okay? And yeah, square root 8, that's just the square root 2 business with the radius, blah, blah, blah. Okay. So I need to set up this new integral. and I need to have some kind of magnitude of v, magnitude of v, and then dt, I guess. But there's still something I have to put here, and I guess we can do this. Not perfect right now. It's really grubby. We need to do something better than this. How do I even start? Let's start with the limits. What kind of limits of integration do you want to see here? So you are wanting pi over 4 to pi over 2? That's what you're wanting? What you're doing is going from here to there. Mm-hmm. So which way do you want it? Do you want a negative in the front, or do you want to switch your limits?
I would switch limits. I just used to have smaller number bottom, larger number top. If that makes sense.
Can I give you something better?
Sure.
I'm not better. Can I give you an alternative? What if I did this instead? Yeah. Now hold on. How can you make that work, Chad? Bad, Chad. Bad. Well, I'm not using what you think for my circle equation. You see, normally we always say x is equal to r cosine and y is equal to r sine, right? I'm saying no. Let's do something a little different. Let's say that x is equal to sine this time, and that y is equal to cosine. Now, I want to do this only because I want to challenge you. Definitely your way will work. Definitely your way will work. You didn't say anything. But but I want to challenge you because I want to show you these little tricks that are important on other problems. If you use this style, what you're actually doing is starting from north going east. It's bearing. You've heard that before with the boats and the planes, bearing. That's what these formulas will do for you. Therefore, what I would say is 0 to pi over 4, because this is 0, and then we're going to 45 degrees there. 4, and then here it is. X is now r sine theta squared, and then y is r cosine theta.
So I have a question. Is it kind of like trying to find like I keep referring back to the squash method, basically rotating onto the x-axis instead of it being on the y-axis?
Maybe.
Okay.
Shooting from the hip again. Huh? Yes. Yep. I'm swapping x and y. So in a way, I'm doing an inverse. Notice that our inverses, I'm drawing the same picture like 5 times. Inverses are about the y equals x line. And so if I had my start point here and I went that way, when I invert it, switch x and y, I technically would start here and go that way. See how that works? That was excellent. I never thought of that. Oh, you said, you interpret it so much more, just more. Okay, good. So they're just a theory. It's just a theory, right? But I'm still at a loss. I don't know what to do here, right? And so I guess what I can do, if you want to be a little bit weird about this for a second, it's technically x prime squared plus y prime squared d theta. Do I have a formula for x and y right now? Could I find their derivatives? That would be a yes. I don't like what I'm doing right here, though. Do you see this right here? What is r? What's my constant radius? 4. Yeah, 4. And I'm like really annoyed by this format, but it's going to be okay. It'll be okay. What's my derivative? If this is my set of equations, what's my derivative then of x? That's a sine, so it's now a cosine. Thank you. Whew. I let that one hang too long. My derivative of cosine will be a negative sine 11 d theta. Oh, I ran out of room. drawing all these silly little... They're all the same picture 5 times. Okay. I think I can simplify this a lot, like right now. In fact, right here, I'll wait. This is equal to what? All of that, dude. Mm-hmm. Bam. So that's nice. And what do these guys have in common? A 4. Now, that's not the only thing they have, but it is the thing they have in common. So I'm going to start right up here now, I guess. I have a 4 from these guys and a 4 from here makes 16 in the front. It is important to do the numbers in the front, because if you don't, you get a whole lot of blah, 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 like I had. What's left over would then be 4 sine squared theta minus cosine theta d theta. Like, that's it. Not too bad, actually. All right, what's your integral of sine squared? Exactly, I use the formula. Wait, you already know it?
I do the identity where you break it up into 1/2 plus.
Okay. No, I'm sorry. I'm sorry. I'm sorry. It works. It works. Right. It's 1/2 and then theta, and then is it a minus? For the sine, it's a minus. For cosine, it's a plus. My. We use this formula a lot. It's a good thing I'm going to write that down on my formula card. Negative cosine will go to... Very good. Very good. You got it. Oh, wait. Bad, Chad. Bad. When you integrate, you don't have to have the integral anymore. Duh. Just put a bar at the end. Yeah, that wasn't too bad. So I've got 16 times 2 would be a 32 theta. Same thing for this guy. I would have 32 sine cosine. And then here, I just have a 16 sine. Plugging in the pi over 4, dividing it by 4, I think we get an 8. Oh, well, you already have the answers. Plugging in pi over 4, this is where I actually got it wrong earlier. So we already know we got square root of 2 over 2 and square root of 2 over 2. Yeah? I said, well, that's square root 2. No. That's 2 over 4, which makes a half. And then finally plugging it in here, we just get square root of 2 over 2. Half of the 16 will be an 8. And you can see the 16 in the middle there. So we're done. We did it. Yay. Cool. Are y'all okay with this one? Was it nifty to see the switch X and Y thing I did? Yeah. Okay. Just wanted to toss that out there. I wanted to show off that I had a master's in mathematics. No, it's just like, nah. None of that really helps me here, by the way. That's fine, though. Cool? Good? Okay, good. Any questions? Okay, let's do another one. I did not prepare this one because I ran out of time. So I'm going to... Oh, wait. I'll leave this up as long as you want. Oh, you're done? Okay, you're done. Okay. So the next one I didn't even do. So we have a wire, and they want to find the mass of the wire. This is a line integral, okay? If you think about what we've done here for a little bit with the line integrals, we have some kind of line in 3D space, and I'm wanting to find, so that's its shadow, I'm wanting to find area underneath the curve, essentially. So you're thinking, oh, well, that's different than the mass of a wire. Well, what it's doing is this is the variable density of that wire. See, it says the density is given by this, which is, well, that's a variable. So variable density of a wire. Therefore, like here, it's thin, but as we keep going, it might get thicker. That's kind of what the idea is. It might bend and twist. So if it does this, then it's like super thick right here and kind of thin right there on the edges. Who knows? I don't really know. But the line integral takes care of that. Cool. Okay, so yeah, mass of a wire. Very cool application of line integrals. So we got a semicircle. Notice that it says positive right there. Happy days, huh? We got this guy. Is that it? Nothing else? Have fun. Go and do it. Should this be a you do? I think it's a you do. You're already doing it. Well, Mason's already been doing it. Beautiful, beautiful. It's beautiful. Yeah, try that out. Try this out. It'll be fun. Do not write DS. Nobody needs a DS in this thing. Unless you want to be full. It's fine. Yeah, we're like shooting from the hip. That's what we do. Okay, straight. Shoot from the hip. It's fun. They're learning what college life is all about. It's about play and eating food outside and planetarium shows. Because that's what we do here. Coffee and solo cups. Maybe I'm having y'all do it so that I don't have to. Yeah, I really don't like the way I'm going down this road. It looks very dangerous. I hope that y'all are doing something different than me because I don't know. Okay. I'm so tempted. I'm going to do it. I'm going to be so bad. Let's just see what happens. wonder if I could just change my limits real fast and everything will be fine. No, don't do it, Chad. Don't do it. Don't do it, Chad. See, now I have to use a formula. Isn't that sad? Nobody wants to do that. Oh, and it's such a terrible formula, too. Do not do what I'm doing. I don't think this is a good road. I know you've done it before. You're like driving down like a road, and then it turns into like a dirt road suddenly. You're like, no, I think this is fine. I think my friend's house is right down over here. And then then it gets like really bumpy. It's been a long time. Then it gets dark, and the clouds come out. And then you start getting scared. How do I get back? Muhahaha. No, you don't need narrative in this class. Please tell me to stop. You're like, no, go on, Chad. It's okay. Go on, let's just see. I'm leaving a lot of blank room for the real answer here in a minute because this is insane. Arc sine 1. That would still be a 0. Okay. 9 times 6? I should know this one. Is that what you got?
No, that's 9 times 6.
Did you get that? Good. Oh. Did you get 36? You either got it or you didn't. So all of this was wrong, and we're going to do something else. And that's fine. Did anybody get 36, though?
I got the closest I got was 32 square root 2.
Then you are not right. It's either right or wrong. This is a math class. Okay, so this road here was not fun. And I don't want to talk about what I was trying to do because it was wrong. So let's not do it. Is that okay? Let's try something else. I am going to go with a polar form this time. So the rectangular mode was just not happy. See, we can convert this to be r squared is equal to 9. Seems easy enough, right? So I want to convert this whole thing to polar. I'm going to go from 0 to pi of, and then I have 2y, so 2 times r sine theta. And then again, I have to have that magnitude of v thing, which we'll talk about here in a minute. That's technically is that a vector? No. Yeah, because it's a magnitude. Yeah, so it's a magnitude of a vector. Yeah. R dr. Oh, can't do r dr d theta anymore. Polar. Yeah. But I think I'd have to have it like this. Because it's that okay, give me a second here. No, we're not going to do that. No, we don't need a required anything. No, we're just going to do it. It'll be fine. Okay, so that's what I'm thinking that we're going to do. I'm just taking a guess. Again, I didn't get to do this before class, so I'm a little weirded out too. There's technically a formula for this one in polar form, and I think it is r squared plus r prime squared. I think, but I'm not 100% on that. I'm going to put a question mark on that guy. Instead, I'm going to try to find it. Well, hold on. Wouldn't we have sine and cosine just like last time? And it would end up being like 3? Technically? No. You don't like that? Right here, magnitude of v. I'm saying like derivatives and stuff. Didn't we have something similar to this before, where it just ends up being the radius? So then I could say that this ends up being a 3. Do you mind if I try that? Is that okay for you? What's my r here? Because I'm doing d theta. What's my r there? It's also a 3. Oops. Okay, so I got 3 times 3 is 9 times 2 is 18. So I got 18 in the front, integral of sine d theta 0 to pi. You're seeing the 36 now, aren't you? Yeah. What's your integral of sine? You're right. Yeah. And then when I plug in a pi, I get -1. But 2 negatives will make a positive in the end. Minus, when I plug in a 0, I get 1. But then I have this negative here. 2 negatives make a positive yet again. 36. Look at that. So all that was wrong for sure. But this formula was not needed for this particular case anyways. But if you notice, if you did this kind of like formula for a second, my radius is like a 3 basically, and I'm saying that my derivative of like whatever I would have would be, I guess, nothing. So then you would just say the square root of the square. It's like absolute value of your radius. Absolute value of 3. There you go. And we just did the first part. Do y'all even attempt the second part? Me neither. You've been watching me the whole time. Are y'all okay with what I just did there? So just real quick recap. I'm thinking polar mode 0 to pi, and then I got 2 times y, and then this magnitude v thingy. Well, we've seen in the past where this turns into, it's the radius essentially. We know that our r is 3, it's a constant. And it's just simple integral. Done. Cool, right? Now that I get to erase all this other stuff here. So they're saying the center of the mass of the wire. Look at this wire. See that wire? Yeah. Do you see its variable density? It's dependent on y. And we're wanting to know, where is the center of mass? As in, if I can hold this wire up with my finger, where would it balance? My first inclination, the first thing I'm thinking is like right there. Okay? But it wouldn't work. Because over here, it's basically 0, but here it's really thick. So like it's like a little bit, and then it goes like thick, 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 and then it goes down to a little bit again. So you're thinking, yeah, that'd be fine. But it's not going to be on the wire. The problem is that the center of mass for this wire is going to be off the wire a little bit. Hey, Chad, how can I balance a wire on my finger if it's in visible space? Mathematics. You could do it in Mathland. Just don't try to do it at home. Yeah. The center of, like, a perfect example of this. What if I had a donut? Where's the center of mass for the donut? It's in the center here, right? It's missing. I like that. It's missing. Yeah, it's missing. So if I tried to balance a donut on my finger, it would go on top of my finger, right? It would just slide down, and then it gets sticky and gross. So, yeah, that's the idea. There is some times where the center of mass will be in just invisible land, and that's fine. How do we find it? Now, center of mass, as you know, is going to be this guy right here. But oh yeah. So, but we already have half the answer. Come on, what's right here? I'm like literally indicating what it would be. Okay. Right? I mean, because there's no difference in my x. Negative x, positive x, it's going to be the same. It's the y that I'm concerned about. So this is the only thing that I'm really concerned about. Let's of course flash the answer and see. You can see it, right? No. What is this? This is x and y, isn't it? Doesn't that look a little weird? You think that. See, that's exactly what I thought. But it's a value. This is not what we're talking about at all. We're talking about a distance. So basically 9 over 4, right, is about 2 and some. And so the radius was 3. So this is 3. We're talking, and so there's 2, there's 1. It's about right here. It's 2 and some. It just so happens to look like a unit circle value, but it's not. Kind of weird, isn't it? Okay, good. So yeah, we're looking at basically the approximation would be about 2 and some. All right, let's do the math then. So y bar would be double integral of y dA over double integral of dA, essentially, right? Here it is. That saves a lot of time. So in a way, I have to do the same integral I just did here because this was good, right? Look, you can see the same thing. All I need to do is add a y in there. And so if I added a y to this right here, rather, well, no, I want to do this one. This one's a good one. Then it would look like 0 to pi of 2 times 3 sine theta squared now times 3 d theta. I'm squaring that y value because now it's not just y, it's y squared. It had a 2y. I have to put another y in there. So y squared. Are y'all seeing what I'm doing? Like I have to multiply by this y here now to make a y squared. Okay. So we get a little bit different number. We got 9 and 3 makes 27 times 2 is 54 of sine squared. And it's a good thing I wrote down that formula again. It's like one of the more common formulas we use in this class now. Like I've even memorized it. And you know how can I say stupid? How stupid I am. So if I can do it, you can too. Great. Y'all weren't taking that. That's fine. It's okay. I'm using every bit of intelligence I can. I just don't have a high capacity. That's the problem here. Because I'm using what I got, bro. It's because I've been doing it for, like, you're the youngest in this class at, what, 21, 22? 22? I've been teaching here for 17 years. I've been doing math like this for way more than that. Right? So I'm using every bit that I have, but you have more potential than me, so that's good. Is that making sense? You still don't believe it, but okay. So half of 54, 20 what? 27? See how fast you were? See? No. Oh yeah. Oh, for reals, the whole thing? You're right, and we get a 0 from each of these guys, and then I plug a 0 in and I get that. So 27 pi. I don't think I have a pi, but you're right. Right. Okay, so 27 pi. That's going to be right here then. And I hope to reduce this down to 3/4. So they both have a 9 in common. And yeah, there we go. Got it. Cool. I think that it went so fast, so nice, because we had already done the integral the first time. All I need to do is change one little aspect and we're good. But the harder part is the setup. It's always the setup. Like, how do I even get started on this? So show your hands who got a 36 the first time. I can't, because I didn't either. You know what I mean? Good? Okay. We got some time still. We can't keep moving on, chat. Yes, we can. Yes, we can. So, because you're going to want the time to review, and you're going to want the time to go over these Stokes theorems and stuff. You're going to be so stoked when we get there. Anyways, so the circulation and flux stuff is what they're going to be focusing on here. Have we talked about gradients? I thought we did. Okay, so we've seen that before. I'm just triple checking here. Hey, look at these cool formulas, right? Um, this has a DS, so that's not our friend. Nobody likes that guy. This one has a DS. Nobody likes that guy. This one has something different, so we like this guy, and we do. Hi, guy. Hi, man. I would say hi, guy. Hi, guy. You are a guy, so I guess that's okay, right? All right, cool. You caught me off guard, bro. Um, this is going to be your new friend forever. Everybody loves FDR, not the president. I mean, you like him too, I guess, but whatever. This little dr, that's a vector. That's a vector, okay? And what is this dot here is a dot product. It's a dot product. And so it's kind of like you're saying you have your x, y, and z coordinates for your f, and then you're going to dot it with your, like, I guess x prime, y prime, z prime from your r, dt. I don't like this notation, but it's making a little bit more sense. In the more mathy sense, it's kind of like I'm doing this. I'm not going to stand by that and completely, but I am going to say that's probably what the end result will be when we get. Oh, it's right there. Duh! Look at that. Do you see it? This is r prime, dt, and this is just f. Now, notice that it's f of r. You're plugging it in. And your r is going to be determining your x, y's, and z's. You plug them in and you get some stuff. It's really fun. It's actually a really cool thing, okay? What is this useful for is for everything going for the rest of the class. We're going to use FDR for all kind of different things, okay? So it's just a line integral, but special. Cool? Okay, blah, 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 blah. Again, we don't like you, but you're cool. I don't know. And lots of cool formulas. If they give you any one like this, you go to the one that you like the most. You go to the guy you like here. And look at this fun stuff. We'll see him soon. I can't remember exactly if it's a variation of this to make Green's theorem, which is another 2 sections away, I think. So we'll talk more about the cap M, cap N stuff, but not today. We don't like you, so we do this, and everyone's happy again. Yay! Different. Brew, brew, brew. It's not the same. It's not the same. You see how we have a T, and now we have an N? It's different. Yeah, we'll still probably just do an integral here, FDR. Yay! No, I don't know. We'll see that. Is this it? Is that the Green's theorem I'm thinking about, or is that just a variation of it? We'll see that later. I don't want to talk about every one of these formulas. Let's just do it. Gradient. And then actually do it for reals. We got time for this. Okay. What's my derivative of ln? 1 over stuff. Have you been watching my videos for the past 3 years? No, 2. Yeah, 1 over stuff. Exactly. So 1 over stuff. I mean, it's just a copy paste. And then I have to take the derivative of that stuff. And so in terms of x, what would that be?
2x over 2x over x squared plus 4y squared plus z squared.
Yes, that was perfect, actually. Well, okay. So, comma, and this is a vector, of course. Duplicate it, like you said, for each one of them, and well, that was it. There's nothing else to do. It's just annoying that you'd have to type it 3 times. Oh, good. Yeah, copy paste. That's high technology right there. Gosh, man. Hmm? Oh, look. They did that. They got me. They did that just to make me upset. That is so mean of them. Thank you. There's a. Oh, no, I wanted an orange for that one. So, yeah, there's a 4. There's a 4. There's a 4. And then so there's an 8 right here. Thank you. Isn't that just mean of them? You go through the whole test, you forget about the 4. Okay, let's actually do some real integral. We got 3 minutes, it's plenty of time. So, notice that we have a dx sitting here. That is phenomenally awesome. I would love to do some more, like, not that guy, like this guy. This is my FDR stuff, okay? So we can't, I want to do them right now. I want to do this guy. Do you want me to skip them, or do you want me to just go in order? Or do you want to just leave now? You want to just leave now, I know. Okay, I won't do it. I won't do it. We don't have enough time. But the dx is a little different, okay? But what we're going to do is follow it exactly. When it says dx, it means derivative of x, okay? We're not going to do it. I'm not going to do it. I'm just saying that's what we're going to do. It's going to be fun times, okay? Good? It's almost too easy. Thank you, guys. We'll talk about that later. Peace out, homies.